Okay, welcome back, everyone. Please take our seats. Our next speaker is Maia Vergniory. So please, floor is yours.
Okay. Thank you very much for the organizers, wherever they are, for inviting me to give this talk and for everyone staying for the last talk. So I'm gonna show you in this talk how, by considering the single particle picture, either in block wave functions with specific pseudopotentials or using Green's function formalism, how can we design and identify correlated topological materials? So one of the reasons why we do topology and condensed matter physics can be identified in this book of Grigory Bolovic, The Universe in a Helium Droplet, where he claims that a helium droplet has its own universe by itself. And this is what happens in topological materials. We look at the topological materials and we can find features that could be related to high energy physics, like the gravitational anomaly, where in the universe it can only be measured in the ring of a black hole, which is very difficult to reach, but we can find the signatures in a lab. Or the Majorana fermions that has been discussed during the school, or even further, the axial Higgs modes that were also, those excitation were predicted in a Weyl semi-metal some years ago. And of course, we have the Weyl and Dirac fermions that you all talk about, axionic responses, the chiral anomaly. So it's a very fascinating field, not to only look for applications, but also to find and give a solid ground to the standard model. So we can have correlated topological materials and topological materials with weak interactions. And I wanted to give a broadened picture, which is very, let's say, approximation zero in rigorousness, but that you know where the materials that I'm going to talk about are located. So we can classify topological matter by using the topological entanglement entropy, being n the number of degenerated states equal to the e to the gamma to the genus invariant. So because in topological materials we can have one ground state or several ground states. So when we talk about topological insulators, we are at gamma equals 0, and we find the integer quantum Hall, the spin Hall, the 3D-TIs, anomalous quantum Hall, etc. And when this equation is fulfilled, and we have more than one ground state for gamma different from 0, we also find interesting phenomena like the abelian fractional quantum Hall that has been measured in gallium arsenide and graphene, for example. But there is another regime when n is smaller than this quantity, and in this particular case, we have the non-abelian fractional quantum Hall effect and non-abelian anyons that are very useful for universal quantum computers. So in this talk, I'm going to stay here for gamma equals 0, and despite that, despite it only having one ground state, we have a very interesting physics. So we're going to have topology combined with magnetism, heavy fermion physics, superconductivity, and mode physics. And all these cases, we can actually tackle with a single particle picture to a certain extent. And I'm going to talk about a few examples because what I do is look for material. So in the first case, I'm going to talk about mode magnetic insulator, nickel disulfide. In the second case, about the new family of topological materials that displays mass enhancements at steel, we can recover the topological surface state. I'm going to talk about iron selenide, how under in strain we can actually make it topological, having a potential new topological superconductors. And in the last part, I'm going to talk about the new formalism that we have developed in Sherbrooke to tackle the mode physics. Okay, so let's start with the first case, and let me introduce what is an abstracted atomic limit that I think it was discussed during the school, but this could be another point of view of the same problem. So an abstracted atomic limit happens when our atoms sit in a Bikov position that are part of the lattice, but some electrons are localized somewhere else away of the Bykov position of your lattice, for example, in the 1A position. So when this happens, and we want to cleave our crystals, some localized charges are going to remain at the surface, or another way of understanding it, if you want to go from this phase to this phase, where the charge is completely localized in the atomic site, you need to close the gap. So the surface state comes from the fact that we have an obstructed atomic limit. And the obstructed atomic limit leads to something called the filling anomaly, which it has a very exotic name, but what it means is that the filling, because some charges were localized away from the atomic site, the electron counting and the band connectivity has changed. So we should have a metal, but we have an insulator. And because we have an insulator, what we're going to find is some charge localized at the surface. And this, because this charge was unexpected, is what is called the filling anomaly. Now, this can happen in different ways. It can happen in the surface, like, for example, here, we have an atomic change, and we have the filling anomaly at the end of the change. Or here we have it in a hinge. Okay, so might happen that our filling anomaly can be at the surface or the corner, or also at the hinges, and this is going to be the case of nickel disulfide that I'm going to talk about now. All right, so nickel disulfide is a very interesting material because it's a charge transfer insulator or a mode insulator, and despite having quite large gaps, hinge states, surface states have been measured with STM at the step edges with the unknown origin. Moreover, it has two magnetic structures. The second one identified in this work by the guys in ISIS doing very sophisticated power neutron diffraction at the time of flight diffractometer. So we have two magnetic phases. One is the cubic, with the very interesting case that all the magnetic moments follow the bonds. So we only break time reversal symmetry, and the spatial symmetry of the cubic structure remain. It's an antiferromagnet, maybe an altermagnet too. And the magnetic transitions go to an orthorhombic one, where we get some sort of a spin Kagome lattice that is ferromagnetic. Okay. So in order to understand where these step edges of the hinge state come from, we start doing analysis of the bulk band structure. So with DFT, we get a very small gap where bands are almost touching, but still we have a gap between the bands. So by using a more sophisticated pseudo potential and increasing a little bit the magnetic moment, we managed to get the resolution of the gap, the experimental resolution of the gap. However, the symmetry of the gap doesn't change. The symmetry that we have in this gap is the same symmetry that we have in this other gap. So in that sense, we are relaxed that we didn't change the physics of the system. And what happens in this gap is that the nickel atoms are localized in the corresponding Bykov position, but the centers of the sulfur atoms are moved away. So here we have the sulfur dimers, and it happens that we have a charge in the middle of the covalent bonding. Okay, and this is what we can actually figure out by doing the group theory analysis. So we have an obstruction to the atomic limit when it comes down to these sulfur atoms. Okay, so now we start this collaboration with experimentalists because DFT sometimes works, sometimes it doesn't work for magnetic materials. And our experimental colleagues managed to actually resolve very clearly the two surfaces. So here is the sulfur termination, where we can see very clearly the sulfur dimers. And this is the nickel termination, where we can see how the nickels form this square lattice. So if we apply the STM, it happens that at the sulfur termination, we see nothing. And at the nickel terminations, we see a small peak. And the The blue lines correspond to the tip getting into the bulk. Okay. If we look at the DFT calculations, what we find is that for neither the nickel terminations or the sulfur terminations, we see any filling anomaly. We have surface states, but all the surface states are unoccupied. And it makes sense because actually the place where we could find the filling anomaly owing to the obstruction of the atomic limit would be by breaking the sulfur dimer, which is clearly impossible to cleave. So, so far we reproduce the STM calculations. We don't see much happening at the surface. But now we go to the rods because in any case, these step edges, this hinge state at the step edges have been measured and there must be some origin. And when we go to the rods for these two different terminations, what happened is that in the nickel terminated rod, we do see a contribution of the charge close to the Fermi level, where we don't see this contribution of the charge in the sulfur terminated rod. Okay, so this actually can reproduce what the STM experimentalist saw in this experiment, that for determination of nickel, they see some contribution at the step edge, no contribution at the surface. And what they also observe is that these step edges were actually very robust in the presence of a magnetic field. And why they were very robust in the presence of a magnetic field, it can also be explained by means of group theory, is because when we apply a magnetic field, we make a phase transition to another group, and our obstructed Barnier charges is split into two Bikov positions, but they remain pinned to the same side, which means that even if we apply a magnetic field, the charge doesn't move, and this is why we still see these step edges originated from the obstruction of the atomic limit. Okay. Any question? No. So we're gonna move to the next case, which is the combination of heavy fermions and topology. And so many people working on this topic because now there are more and more materials where they measure a gap in the bulk and then they measure a surface contribution, and it's very difficult to explain the origin using DFT. So what I'm going to explain here is how sometimes using DFT we can actually say something about the origin of the surface state in heavy fermion materials by taking into account the electron counting of the broad wave function and comparing to the electron counting, to the symmetries of the many-body wave function. So from the group theory point of view, this problem was interesting because, of course, as we know in heavy fermion materials, we have flat bands from localized electrons that are crossed by dispersive band from itinerant electrons. And when we have this situation, hybridization might happen and we can open a gap. And when we open a gap, all this group theory analysis that we can do comes into place because we can analyze the symmetry of the gap and see whether there is topology or not. And something very interesting that happens in these systems is we have what is called cumulative topology. So cumulative topology means that whenever we have a topological gap with topological bands, this will persist in every gap till we find a gap with the same invariant, and then they will cancel out. So in the case of having F flat bands crossed by a dispersive T band, for example, we're going to have many gaps. And we only need one gap to be topological in order to have a bunch of gaps that are topological. So it means that at least you have some freedom to even move up and down below the Fermi level. And this is something that came from all these high throughput searches. And this is what we expect to find in this type of heavy fermion materials. So the first example we look at was samarine hexaboride, because there were surface state measured by ARPES. And even though it's insulating in the gap, it has some contributions in the surface. And this could be one of the explanations. So samarium is very interesting to study because it has 5d and 4f electrons that are quite isolated from the rest of the s and p orbitals, and it's a mixed valent compound, which means that the filling oscillates between f5 and f6. And this filling is very interesting and very convenient for us because it's 2 electrons short from the half filling. And because it's 2 electrons short from the half filling, it happens that when we look at the Bloch wave function, the symmetry of the Bloch wave function is L plus minus 1/2. And if we look at the spectroscopy measurements, it happens that the symmetry of the many-body wave function is 5/2 of 7/2 minus the singlet, which is very close in energy. So we can consider that this is 5/2 of 7/2. So it happens that the single particle Bloch function and the many-body wave function, they both share the same symmetry. And because topologies is one of these very rough properties of materials, if the gap has the same symmetry, if the gap has the same symmetry for both the many-body wave function and the Bloch wave function, in principle, our machinery should work. So we did DFT calculations with one of these elaborated pseudopotentials, and here we can see the F flat bands, and here we see a D band that is crossing all the F bands, and they are hybridizing, and here in this region is where we get many gaps. So we do group theory analysis by assigning all the irreps and getting the symmetry indicators and all that. And what we found is that there is a lot of topology around the Fermi level. So the first gap appears at minus 0.5 with many types of different indices. And this gap is carried out to the gap at the Fermi level and to the next gap above the Fermi level. So one of the indices, the C4 pi m equals to 4, for example, means that we have a mirror term number of term number 1. So we did a tight binding model to calculate the winding of the Wilson loops that we see here. And what we saw is that 2 surface states, one at X and one at gamma, which is what the ARPES experimentalists measure. So since samarium works nicely with DFT, we expect it to work also nicely in other families. And from this topological quantum chemistry database and these high throughput searches, we identified 3 potential interesting candidates that are R for rare earth, arsenicum sulfide, and we found this could be realized for yttrium, lanthanum, and samarium. And this was done with Inigo, that was my student, Eteri from the Max Planck, who grew the materials, and Chimiao, who did the heavy fermion analysis. Chimiao and his group. Okay, so don't know if you can see it here. It was reported in a monoclinic structure experimentally, but it happens that the structure was not properly refined, and high-resolution X-ray diffraction with synchrotron showed that it actually belonged to an orthorhombic group, the PNMA, the number 62, that actually has these layers of samarium and sulfur, and in between we have this distorted square net lattice of arsenicum. So these materials were grown for the 3 cases, yttrium, samarium, and lanthanum, and resistivity measures were made. And in the resistivity measure, interesting results happened because they saw a large mass enhancement for the samarium case at below the antiferromagnetic temperature. Okay, so, but these materials were predicted to be topological insulators in the website, and even though it belonged to a space group with more symmetry, the analysis of the gap said that they were still topological crystalline insulators. And actually, the fact that the lattice of the square net, the square net is distorted, is what actually opens the gap and allows for topology to exist. So the symmetry indicator that we find is C4 equals 2, which means that we have a double inverted bands, and either we have a high order TI or an hourglass fermion protected by Clyde symmetry. This information is contained in this paper of Shida-san. It has all the tables where you can see, depending on the space growth, what are the indices you can get to diagnose your topology. So without the spin-orbit coupling, we have nodal lines with a spin-orbit coupling, and we open a gap, and the glide combined with time reversal symmetry protects the topological surface state. So here we have the hourglass fermions that happens in the gap of the compound. Now we want to understand better where the topology comes from, because we want to do a model, because we want to use collaborate with Chimiao and do slave Poisson calculations to understand whether this topological surface state that comes from the gap will survive to the inclusion of correlations. So it's a very interesting case because all the topology comes from the PC and PY orbitals of arsenide. So the band inversion happens right here in the CU line, and with the contribution of these orbitals. So it's actually a very interesting material because the hybridization between the F and the, let's say, dispersive electrons is not happening between F and the electrons, but between F and P electrons. But group theory allows for these two orbitals to hybridize. So we did, again, going to the paper of Shida, it also says that we can construct with these indices and having a two-dimensional TI, we can make a layer construction of a tight binding model, at least of these bands that are inverted. And this is what we did. So we did first the monolayer, that the distorted square net compounds for with and without the spin-orbit coupling, calculating the windings, and then for the bilayer, with and without the spin-orbit coupling again, calculating the windings, and then when we have the model for the monolayers, we combine them by the Glide symmetry that is related to them, and we can get the full model. And then in the group of Chimiao, they developed this slave boson model to see how the shifting of the bands were happening when we add correlations. And what it happens, and here is the result of the model, is that what the F electrons do is actually shift the surface state above and below the Fermi level, but it doesn't kill it. So if we go at the surface again, we can see these hourglass fermion that have the hourglass shape. So then we did DFT, and with DFT we actually saw the same situation. So the F electrons feel the Fermi level, and what they do is push the hourglass fermion above and below the gap, but they are not destroyed. And the reason why DFT works is because, again, the Samarion has this symmetry of the Mendy-Moody wave function that works, that has the same symmetry of the block wave function. Okay, and the last case is the case of lanthanum, where the gap is so small that we could have topology or not topology, depending on many, in the theory part, depending on the pseudopotential we are using, and on the experimental part, depending on the growing conditions. But under pressure, maybe we can enhance the gap. If not, yeah, we'll have that problem with lanthanum. Okay, so in the second part, I want to talk about topology and superconductivity, but as a very special case of topological superconductivity that has nothing to do with this full classification of topological superconductors made in the bulk. Here we are interested in topological superconductivity at the surface. So we have a topological gap. This topological gap will have a topological surface state. If it undergoes a superconducting transition, we're going to open a gap. We're going to have a superconducting gap. And the superconducting gap by symmetry should be able to hold Majorana bound states. This was predicted by Fu and Kane in already a long time ago. Okay, so iron-based superconductors are ideal candidates to actually look for this feature. On one hand, they are electron interaction superconductors. They have strong correlations, which in principle is not needed, but they are present, so we need to take them into account. And these electron correlations have been measured and predicted by, for example, Amalia Coldea and Bruce Valenti. They have identified the Hubbard bands both with DMFT and with transport, so they have these correlations have been identified. All right, so it happens that if iron selenium is doped with tellurium, so what happens here is that because tellurium is a larger atom and induced some pressure, there is this PC band that goes down, it hybridizes with one of the d electrons, and we get a topological gap. So this topological gap, when we go into the superconducting state, the topological surface state that we find at the surface opens and becomes superconducting. And is this in this gap where we can find, or we should be able to find Majorana bound states in the vortices of the material. So trying to understand a bit better how this iron, tellurium, selenium works and whether it's topological or not, because this is a theoretical proposition, we did a collaboration with a group of CX at Stanford who did ARPES on iron selenium doped with tellurium. And a very interesting thing that was very helpful for us is what is the orbital content of the band. Because like this, we can do group theory analysis and we can identify better what are the symmetries that are taking place into the symmetry of the gap. So what CX told us is that we have two contributions that they are the DYC and the XC orbitals that we only needed to consider into account these two. And then, of course, the PC band of the tellurium orbitals should be somewhere. But what happens is that experimentally, they could only measure the DXC and DYC, and the DFT calculation will have something quite different with let's say, interesting contribution of the PC orbitals that was not measured experimentally. So in order to prove that the surface state is topological, they measure for, this is ARPES, they measure for different photon energies, and the topology, I mean, the cone was still there. And then in order to see this band inversion, they got several cuts of the ARPES data, and they did the spectral weight ratio at different photon energies and in different regions. And what they saw, that this was also very important for us, that they see a band inversion with a PC orbital at closer to the C point. Whereas in this case, the first DFT calculations were telling us that the band inversion, if it was happening, it was closer to the gamma point. So, interesting information we got from the experimentalists. It's a case-independent Dirac surface state. We have the presence of PC orbitals, and DXC and PC band crossing can be observed in the data. All right, so what we did a symmetry-adapted tight binding model by considering the orbitals that the experimentalists told us are playing a role. And then this is very systematic at the moment. So we know that the iron sits in the two Wyckoff position because it sits in the two Wyckoff positions. We know the irreps in real space, and we know the irreps in reciprocal space, and we know how bands should connect. And because the selenium tellurium sits in the two C Wyckoff positions, we also have a lot of information about the real space and reciprocal space. Okay, so by playing around with the pseudo potentials and the input of the experimentalist, we managed to move the band inversion to the C, close to the C point, which is something that the experimentalists were seeing. But still, there was a lot of work to do in order to be able to reproduce the experimental data. And we needed, because this is theory, our tight binding model, and this is the experiment. So from the DFT theory to the experiment, there is a quite long run. So first, and this was the input of CX again, he said he wanted to have all the terms that accompany the spin-orbit coupling together and play with the spin-orbit coupling constant. So we did that, and it happens that if you increase the spin-orbit coupling by 1.5, you get the normalization of the bands closer to the experimentalist. But then, of course, we have this PC band that was still around here, and PC band is something that the experimentalist cannot measure, and that the gap was still larger than the experimental one. And here we could not move forward anymore, but if we would renormalize the gap by the order of 5, not 3, which is the standard renormalization when there are correlations, we can actually get the experimental gap. Okay, so DMFT calculations can reproduce this. With DFT, we can understand the gap and we can understand the symmetries, but there are some renormalizations we cannot reach. However, the fact that we were working with iron, selenium, tellurium give us let's say, a nice understanding of the band structure and how they play. And we realized that the effect of the tellurium coming down with the PC band could simply be replaced by a strain. So if you induce a strain, you do the same effect as doping with tellurium, because tellurium is a very big atom. And if we do analyze the case of iron selenium and the bands around the Fermi level in the gamma C direction where topology could happen, we see that there are many protected crossings. But these protected crossings are protected by this same combination of symmetries, which is the one that relates the A1 and A2. So if we induce a strain and we break these symmetries, going from this square to this, from this tetragonal space group to this orthorhombic one, then we can actually reduce the gamma 6 and gamma 7 E-reps to 1 E-reps and gamma 8 and gamma 9 to 1 E-rep. So now what we're going to have is crossing of same E-reps, and this is going to induce a gap because there are avoided crossings. So for this gap here, we can induce a C43 topology, which is a strong topology, and above, for these ones here, again, we can induce a C41 topology, which is again a strong topology. So by breaking these symmetries, we can induce a topology in iron selenide. So the experimental tetragonal is not topological. By inducing a strain of 1%, we can open several gaps that in the experimental orthorhombic, there are not that many of them. And if we look at the surface, we can see these surface states that are topological. Now, we know that, well, this was the charge self-consistent loop that, in this case, the group of Rosé used, where we start with the Vanier functions and DFT, and we put in a impurity solver, and well, it's a multi-orbital DMFT calculations, and here are the details if anyone wants to look at them. We have correlations, and we know because in the case of iron, tellurium, selenium, tellurium, correlations play a very important role in renormalizing the gap. We needed to do the DMFT calculations that we did for the different cases. And in some cases, the DMFT actually can show that the gap is not closing, which means that the topology in principle will prevail. In other cases, the broadening of the spectral function is so large that there's nothing we can say, but this is what happens with DMFT. But for example, in this case, in some of the bands, the topology should survive. Okay. And in the last part of the talk, I'm gonna talk, this is the previous part was about finding materials that display topology with certain level of correlations. But now we want to develop a methodology that actually can diagnose topology and do a symmetry classification of correlated systems by using the single particle function, because DFT completely failed. And this is a work that has been done by Theo Dion, who is very famous now in Houston. And everybody knows him. And it's actually a very nice work. So we have our model. We're going to start with a model that has crystalline symmetries, because we want to have crystalline symmetries. Is the one-dimensional diamond chain that we have here. But we want to classify different type of modes. And for that, we needed to add a spin-orbit coupling to the system, because as a function of a spin-orbit coupling, we can move the spectral function around and get the symmetry of the bands shifted. So we have two Wyckoff positions again, 2i and 2m. Group theory is very useful. It's a very fantastic tool. And these tell us how the rips should look in reciprocal space. Okay, so what are the tools we're going to use to classify the systems? So one is going to be the spectral function that we can get from the symmetry preserved Green's function. And in this paper, Theo did a full Wigner theorem application to the Green's function to prove that this is actually possible. And then we're going to use the one-body reduced density matrix. So the one-body reduced density matrix has been used widely to calculate the quantum geometry, but no one has used it to actually take into account correlations. And it's actually very useful because it reduced the n-body problem to one-body problem by integrating over the n-1 states. And from the one reduced density matrix, by tracing it out, we can get information about the occupation. And if we get information about the occupation, we get information about the symmetry. And this is, in principle, all we need to be able to at least do a symmetry classification. Moreover, if you look, you play around with the possibilities of the one-body reduced matrix, you can get the orbital distribution by tracing on all the degrees of freedom. And we can also have a purity measure, because if the square of the density matrix is equal to the density matrix, it happens that we have a Slater determinant. And I want to mention that whenever we remove correlations, we get the results that we would get with the block wave function. Okay, so results. So here we have the IREPs, okay? And we can see that phi, which is the phase that we add to our system to introduce the spin-orbit coupling, and it's also very nicely discussed in the paper, we see that we get different IREPs depending on the phase of the spin-orbit coupling or on the value of the spin-orbit coupling, which means that we have actually different modes that can be classified by using the symmetry of the occupancy of the one reduced density matrix. And now, more interesting, if we analyze the trace of the density matrix and the square of the density matrix, we see that for the case of the mod, the contribution of the density matrix is way small than the case where we don't have the mod. And this can actually be compared to make sure that we are right with the DMRG calculations of the same model. What we see is that in the orange region is where we have the mod insulating phases, and in the middle is where we have non-mod insulating phases, although it's kind of a mixed state. And we see that we can reproduce exactly what the DMRG calculates by looking at the trace of the square of the density matrix. All right. So in principle, this method can work to at least classify different mode insulators. So can we use it to diagnose topology, this occupancy that the one body reduced matrix gives us? Well, let's see. And for that, we are using the SSH model plus Hatsuo-Komoto interactions without breaking time reversal symmetry and with two different holdings. So here we will have the topological bands and here the Hatsuo-Komoto interactions. So we have different regimes, which is the half filling low interactions, half filling high interactions, and quarter filling also high interactions. And we want to analyze these different cases. This is a model that is in the literature anyway. So what are we going to see? Before moving forward and doing the EREP analysis that is ongoing project, we want to make sure that we are able to diagnose topology. And for that, we're going to use the Wilczek-C connections, which is a non-abelian generalized phase. And in principle, will tell us the winding of the Wilczek connection, which is related by this covariant derivative to our one reduced body matrix. And another geometric quantity that we're going to look is the quantum volume, which is the volume of the trajectory traced by the density matrix. And this is an exploratory work, so we want to see what we get and if both methods can give us the same information. So it happens that with the winding number from Wilczek, we get, as a function of the intercell hopping, we get a region where the outward chain is trivial and a region where we find topological windings, let's say. And when we look at the quantum volume, we get basically kind of the same result, where there is a region where we find this topological feature which coincide with the winding number of Wilczek. So these give us a possibility to actually explore how these could be used to diagnose topology in real materials. So with that, I'm going to conclude. So there's been different parts of the talk. So topology and correlations offers a rich wide playground to design quantum materials. So nickel disulfide is an unconventional abstracted atomic limit where it can be only measured at the step edges of STM and also gives a response or an answer of the origin of these hinge states in nickel. We have presented a new family of heavy fermion materials with robust topological surface states. Iron selenide can be strain and induced topology, and the study of superconductivity is ongoing. And I have presented a new formalism to diagnose topology using the one-body reduced density matrix. And I thank you all for your attention.
Great. Are there any questions for the speaker?
Hey, Maia, so this nickel sulfur 2, what's the statement that the lattice symmetry is of some particular form?
Well, the statement is that, of course, because of the lattice, we have these sulfur dimers. Mm-hmm. And the sulfur dimers have the charge localized in the middle of the bonding, of the covalent bonding. So this is actually, we have this abstracted atomic limit. So this is actually the reason why they were measuring the hinge state with at the step edges.
I see.
And this this can be predicted with theory.
The reason I'm asking is that I think if you go from nickel sulfur 2 to nickel selenium 2, there's a Mach transition happening, and I wonder whether that could be.
But this is also because it has this magnetic structure. Nickel selenium 2 has the same magnetic structure.
One of them is a paramagnetic metal, if I remember. The other is a Mach inserter, which presumably is magnetic order, and but maybe there's also aspect of in addition to the interplaying with magnetism, maybe there's also aspect of interplaying with Mach transition that could be interesting.
Yeah.
Thank you very much for your talk. When you define like this, like quantum volume or like Winding number, are those like related to like any response function at all, or like is there a way to have like actually probe this quantity?
Haven't studied that. It's the Wilczek winding is the non-abelian very phase.
So would that be connected to have like an interferometry?
Yeah.
Yes.
Yes. Yes, eventually yes, but we haven't done it. And also the quantum volume is related to the quantum geometry. So it would be, I mean, they can be related to transport, but we don't have the equations yet.
Thank you.
Any other questions for the speaker? Yeah.
Hi, thanks. Very nice. Very cool stuff. Yeah, I had a question also about the nickel disulfide. So do you have a picture where you show the three main Wyckoff positions there? There's a 4A, 8C, and the unoccupied ones, right?
No, I mean, you have the 4A for nickel, 8C for sulfur, and then the 4B for the obstruction.
So the idea is that every allowed EBR decomposition requires some weight on the empty 4B Wyckoff position.
Every
Right. Every allowed decomposition, you need some weight on this.
just for the electrons that are localized in the core. Not all the electrons of sulfur are at the 4B Wyckoff position. It's just some of them.
I see. But as far as that position is concerned, I'm just curious about, is this a decomposition invariant, type thing? Is there something different about I guess what is the invariant that that you compute, because there's this Wannier obstructed Wannier charge center.
Yeah,
So there's a bulk invariant that
there is obstructed Wannier center, but probably there were gonna be real space invariant, but we didn't calculate it. This is the moment you get the information about the Wyckoff position is okay for what we wanted to do.
I see. Okay. Thanks. Yeah.
Any other questions?
Hi, thank you for the talk. I also want to know a bit more about this quantum volume, because it seems it's an integral of the derivative of one RDM in some sense. So is there like a intuitive meaning of this quantum volume?
It's all the maths are in the supplementary material of the paper.
Okay, let's thank the speaker again, please.